Okay, so we want to now discuss what it means to be in steady state. So let's explain this with a very simple example. Let's say you have a room and the room has some people inside it, and then there's a door on the left where people can enter, and there's a door on the right where people can exit. The situation of steady state happens when the number of people in the room doesn't change with time. For instance, if you have within 1 minute 2 people come into the room, and during the same 1 minute 2 people leave the room, then the number of people inside the room remains 5. That's what we call steady state. We said what steady state is, but what would it be if it's not in steady state? An example of not being in steady state is if you close this door here and you just let people go into the room. So in 1 minute, let 2 people enter the room. Then in this case, the number of people inside the room is getting bigger with time. So this is a situation of not a situation of steady state. It could be, for instance, that one person, if you wait for 1 minute, one person enters and 2 people leave. In this case situation, if you wait after the 1 minute, you'll only have 4 people inside the room. So the number of people inside the room is getting smaller. So this is not a situation of steady state. And we can give another analogy for the case of steady state, or the flow which is the flow of water in a pipe. Imagine you have a pipe here, and the pipe has a small diameter here and it has a large diameter here. And let's see what we can discuss about water. So let's say you have water going through this surface and water coming out of this surface. In steady state, if we are in steady state, can the current of water through this surface be different than the current of water through this surface? Can they be different or not? Well, let's give an example. Let's say you have here, the current is 10 kilograms per second. So 10 kilograms are going in every second on this, through this surface, and in this surface 8 kilograms per second are leaving. What would happen in this case? Well, what would happen is, if you focus on this volume that is enclosing the pipe plus the 2 areas, the amount of water entering is 10 kilograms and amount is leaving is 8 kilograms in 1 second. That means the amount of water inside the volume is increasing. But how can this happen? Water is incompressible. You can't compress water very easily. It's very, very difficult to compress water. So actually, this cannot happen. The water will prefer to exit here rather than being compressed. And so there's not going to be any buildup of water inside this volume. So this cannot be the case. You can't have the current here bigger than the current here. Okay, what if it happens like this? What if you have current here is 8 kilograms per second and here 10 kilograms per second? What would happen as time goes on? In this case, if you wait for 1 second, 8 kilograms of water went into the volume and 10 kilograms went out. That means the amount of water inside the volume is getting less. It's decreasing with time. This is not a situation of steady state. So this cannot happen in steady state. So if you're in steady state, the amount of water going in per unit time has to be, the rate at which water goes in has to be the same as the rate at which water goes out. That's the definition of steady state. So the current in is equal to the current out. If it wasn't the case, if the currents were not the case, then the amount of water inside this volume will either be getting bigger or smaller. So steady state means that the amount of water inside the volume doesn't change with time. That's what steady state is. The same thing happens if you have a wire and the wire has a different diameter here than it has over here. It's the same idea exactly. Why? Because charges, the negative charges that are flowing in the wire are also incompressible. It's not easy to make the negative charges get closer to each other. So if you look at the charges are incompressible. So the number of charges per unit volume, small n, stays the same. And so it's very similar to the case of water. So you can't get a situation where the current here is bigger than the current here, because that would mean that the charges are going to be compressed closer to each other, which cannot happen. And if the current here is bigger than the current here, then the amount of charge inside this volume will be getting less, and that wouldn't be the case of steady state. So the case of steady state is when the amount of charge inside this volume doesn't change with time. So the current going in has to equal to the current going out. You can look at this PhET animation and try to follow these instructions. Go to this website and download this simulation and follow these instructions to see how it looks in a more intuitive way. Let's discuss the issue of steady state in a more mathematical way. Remember, we had the equation for charge conservation, this equation that said that if the charge inside the volume changes with time, it must be due to the flow of charges through the surface, which means there's a current through the surface. And this equation relates the current through the surface to the decrease rate at which charge changes inside the volume. Okay, what do you think in this point of view would the steady state condition be? When would you be in steady state for this kind of charge conservation? You would be in steady state if, remember, if the total amount of charge inside the volume doesn't change with time. That means dqn by dt is 0. That means integration of j dot dA has to be 0. So this is the condition for the system to be in steady state. The total current going out of the surface has to be 0. Let's go back to the wire and let's see what that means. If you take your volume, your closed surface, to be the wire plus the two surfaces, so this closed volume, the area vectors, remember, if you have a closed volume, the area vectors have to point from inside to outside. And let's say that this is J1, the J vector at this position, is this area is J1, and the J over here is J2. So let's see what this integration gives you. Well, the only place where you have current flowing through this volume is through this surface and this surface. So integration of J1 dot dA, that's the current going out at this surface. Integration of J2 dot dA is the current going out at this surface. Now let's make a simple trick. Let's, instead of writing dA where the dA points from inside to outside, let's just multiply this by -1. You get minus, let's just multiply by -1 and switch the direction of the area vector. So that means minus dA prime. dA prime now points in the opposite direction. And so minus dA prime is exactly the same as dA that we had before. But now in this case, integration of J1 dot dA prime, this is the current going into the surface. This is I in, because the area vector is pointing into the volume in this case. So we have now that minus I in plus I out is equal to 0. That means that minus I in plus I out at 2 is equal to 0. It means that the current going in equals to the current going out. So the fact that the current going in is equal to the current going out, this results from the fact that we are in steady state. And steady state, as we just showed, it means that the total amount of charge inside this volume doesn't change with time. And so that's when the current going in is equal to the current going out. You can do the same thing with a slanted surface. It doesn't have to be a surface at 90 degrees, any kind of surface, but the surface has to completely enclose the whole area of the pipe. You can't let an opening exist because remember, the condition is that the amount of charge inside the volume that you have doesn't change with time. So if you the same thing will apply for these two surfaces. The current here equals to the current going through here. Can you think of a system where the flow of charges is not in steady state? We showed for a wire that the current going in equal to the current going out, and that was in a case of steady state. But what can you think of a system where the charges are not in flowing in steady state? So it's this example, for instance. If you look at this flat surface, there is current going through this surface. There are charges going through this surface. In this case, it's negative charges going this way. But this curved surface, there's no charge going through it at all. And what's happening is that charge is being built up inside the volume on the capacitor plate. So as time goes on, the charge here becomes more and more positive because negative charges are leaving the volume. So this is a situation where you don't have steady state. The amount of charge inside the volume, inside this red closed surface, is changing with time. It's not staying the same. The capacitor plate is getting more and more positive. dqn by dt is not 0. It has a value. And that in this particular case, dqn by dt is positive. So this right-hand side is negative. That means the current through the surface is negative, and you can see that being the case because the area vector is pointing from inside to outside, and the J vector is pointing from the left to the right, and the angle between them is bigger than 90 degrees, so you get a negative sign when you get the dot product. So this is a situation where the system is not in steady state.